What is German?
I thought
Dude,
Spanish was
it's-
bad.
Yeah, I thought Spanish was bad.
What's bad?
German.
Was.
No, not the actual language. Yeah.
Uwe was.
Oh,
Warum?
what? What are you asking me?
Warum?
Room?
Warum? Why?
That's what I figured.
It's January. You don't know who, what, when, where, why?
No, I don't know it in German.
Really?
We don't take German.
Who?
I'm not in German.
Oh, okay. Well, that explains it then. Like, how
I'm in
could you
German.
not
I
know
don't
that?
know it. Me
This
neither.
one is.
Me and Chan.
Jenna, who? Who in German? Oh, dear Lord. What mess have I got myself into here? Do you know the interrogatives?
I know
Know
we were
the
supposed
who,
to
what, when,
learn
where,
that.
why? Yeah.
Yeah,
Okay.
but
All right. My faith in this conquest has been restored. All right. We're going to finish up this one little lesson. There's only a couple slides left on this one, and we'll jump right into the next one. The next one's kind of short, so I'll be finally back on track. I should be able to finish the second one. All right. We left off with a question, and it's a pretty profound question. I truly don't want you to spend the rest of the day thinking about how profound the statement is, but I'm going to make it anyway. So where did we leave off? We were talking about electromagnetic radiation, and key point to remember is that all electromagnetic radiation travels at the speed of light. Now, yeah, we throw that out there really, I don't know, carelessly, and sometimes we don't stop to think about what does this mean or what the implications. The speed of light is, it's not just fast, it's unimaginably fast. So fast that I need to put this in numbers. Generally speaking, when we try to wrap our head around something, you throw some numbers out there. So for me, this is the number right here, 671 million miles per hour. That is the speed of light. If we talk about it in miles per second, 186,000 miles per second. The Earth itself, the circumference of the Earth around the equator, or any of the meridians, is 25,000 miles. You do that math, that means that light goes around the Earth not just once a second, not twice, but I believe it's, I have a slide here in a second, 7.5 times per second. Yeah, Matt.
You need to write down the numbers.
No. This statement right here, absolutely. All electromagnetic, we're talking about from the radio waves all the way through the gamma rays, everything in between travels at the speed of light. But it's just this concept that we talk about in science, but we never really give it some thought. Now, scientists always operate in the metric system. So 300,000 kilometers per second is generally, you'll hear it plenty of times in this semester. That would be roughly 300 million meters per second. A meter, this is a meter stick. So 300 million of these per second, that's the speed of light. Very fast. Three quick, they're just gifts. So this is the speed of light going around the Earth, right? That's literally how fast light goes around the Earth. 7.5 times per second. We think about fiber optic lines, the internet, Wi-Fi, that sort of stuff. You know, at least in my generation, you had these things called pen pals. Oh, there's a little kid in Nigeria that I write to, and the physical letter goes from my hand to his eyeball. Now, in the age of the internet, I mean, literally, it's not. It used to be a big thing to have a pen pal from a different country. Now it's like every single night. Get on the PlayStation. I don't know. I'm playing some idiot from Germany, right? And some little 7-year-old kids cursing me out on the PlayStation. That's what the mute button's for, right? But point being is that what allows for me to literally play a game with someone in Germany or wherever is the fact that light travels so fast. If that wasn't the case, then we couldn't play games together, right? Second one is, okay, that little white dot going back and forth, that represents the speed of light, a signal going from the Earth to the moon. Average distance, about 250,000 miles away from us. One more time, sorry. back you. There we go. So that's long. If you ever watch any of the old movies of the space landings on the moon, the Apollo landings, you'll always hear this huge pause in between. Hey, didn't he just ask you what's up? And there's this pause. Didn't you hear him? It's because the speed of light, as soon as we interject some distance, all of a sudden becomes something that's of a consequence, meaning that we got to think about how long it takes for light to get from the Earth to the moon and back. When we think about more larger distances, just within our solar system, the picture in the back of the wall there, this slow moving white dot is a radio signal, light, laser beam, whatever you want, anything in the electromagnetic spectrum going from the Earth to Mars at its closest approach. And the two orbits, when the Earth and the moon, or the Earth and the Mars are its closest approach, it still takes 3 minutes and 2 seconds. That's why we can't have that rover there driving like with a joystick. There's a commercial a couple months ago about, I think it was a Lexus commercial, or it was some car commercial that had a guy driving the rover. That can't happen. As soon as you say turn left, at its closest approach, you got to wait 3 minutes for that input to go to the rover. At its farthest approach, I want to say it's like 20 minutes. When Mars and Earth are separated as far apart as they can, it's about 20 minutes for a signal to get from the Earth to Mars. Craziness, craziness. That white dot in all my talking still isn't even halfway there. Part of these 3 slides is to, you got to be ready for this. This is philosophically kind of deep. So it turns out that when you look at the night sky, you are not looking at the present, you're looking at the past. The light from Mars at its farthest approach takes 20 minutes to get to your eyeballs. When you point the telescope at Mars, you're not looking at Mars, you're in a time machine. You're looking back in time at its farthest approach 20 minutes ago. If Matt has a ham sandwich in his hand and he's on Mars, he'll die because there's no oxygen. But if he was there and he theoretically could live, if he eats the ham sandwich and I'm on the Earth pointing my telescope at Matt, I don't see him eat the sandwich until 20 minutes later, when he's already finished the sandwich and now he's, I don't know, drinking a Diet Coke or something, right?
I like that.
Okay.
Realize my.
This is craziness because Mars is close. Once again, my favorite picture here, Andromeda Galaxy. It's over 2 million light years away, 2 million light years away. When you see this beautiful picture right here, you're not looking at Andromeda. You're looking at what Andromeda looked like 2 million years ago, over 2 million years ago.
Much closer now.
It turns out we don't live in the present visually. We don't. We can never observe the present. Even right now, it looks like Danny's got his pen in his hand. Or pencil, sorry. I'm looking what was in his hand in the past, not what is currently in his hand, right? I'm looking past. Now we're about, I don't know, 10 feet away. It turns out that light takes about a billionth of a second, a nanosecond, to get from 10 feet. It goes one, I believe it's 1 nanosecond. It takes for light to go 1 foot. So if he's 10 feet away, that's 10 billionths of a second. So yes, in all, for things that are very close to each other, yeah. I mean, this is how I'm able to catch this, even though my eyeballs aren't really seeing it. They're looking at where it was in the past. Craziness. Yeah. We can never observe the universe. We can only observe what was. And if this isn't a statement that causes you a little bit of lack of sleep, you don't understand what it means. We don't look at the present. We only look at the past, including right now in this classroom. Sound is even worse, right? Sound waves travel much slower, much, a order of magnitudes slower than light. You don't ever hear my voice in the present. You only hear it in the past. You never hear what I'm saying. You only hear what I said. It is madness. Okay. Lastly, information is always contained within this electromagnetic radiation. This is why we observe it. These three, all of these right here.
Oh.
This is why we do this. We want to know something about the Andromeda Galaxy. We're never going to be able, at least in our present technology, to get to the Andromeda Galaxy. It takes too long. We can't even go at the speed of light. And even if we could, it would take 2.5 billion years to get something there. And if we're waiting on a signal to get back to us, we'd have to wait another 2.5 million years. That's not going to happen. Therefore, we need to look at what does reach us. That electromagnetic, the radio waves, the infrared radiation, the ultraviolet radiation, the visible light. All that stuff is coming to us from Andromeda Galaxy. And inside of that is that information. What does it look like? What color is it? How hot is it? All of that type of stuff, that information is contained within the electromagnetic radiation spectrum that we receive from, for instance, the Andromeda Galaxy. Okay. Questions? I'm not.
Is it possible for us to go faster than light?
According to most scientists, the answer to that is no. No, I would, just as Copernicus was sure of his idea of the universe, I'm not going to go out on a limb and say I'm neither smart enough nor able to see that far in the future to predict if that's true. It is certainly, of everything, it's the holy grail of science. Can we ever travel faster than the speed of light? Currently, the answer is no.
I mean,
You can't even write correctly. I'm so like dead now.
Matt, as you look at the paper, you're not really looking at the paper.
No.
You're looking at what was there a few billionths of a second earlier. I blame the speed of light on my bad penmanship because I can't see what I'm writing. I'm only looking in the past.
That's why my hand.
that billionth of a second is throwing me off, man.
All right, we good?
Yeah.
All right.
My math brain is good, but.
All right. Next lecture. Oh, I like this one.
You're gonna be drinking something in the past. All right. Janie just doesn't care anymore. She's just reading his D&D books. Just doesn't care. He's just like brain.
Okay.
Doesn't anymore.
So another day is like, didn't we just have a lesson on electromagnetic spectrum? We did. It continues, another part of it. All right, we left off. Remember, we're talking about electromagnetic radiation, comes in many different flavors, but that radiation is made up of two parts, an electrical field and a magnetic field 9 degrees off from each other. If we look at the spectrum itself, starting with the longest wavelength, radio waves on the left, gamma rays on the right, it's a continuous spectrum. Like I said, these are man-made human words that we use to describe them: radio waves, microwaves, infrared, visible light. The waves themselves don't really understand which one they are. They never stop. But those are the names we give to them. All parts of the electromagnetic spectrum, they all travel at the speed of light. They all have amplitude. They all have wavelength. They all have frequency, right? Some of them are not harmless to humans, luckily for us, visible light, unless you turn the light bulb way up, then usually it's more harmful because your eyeballs can only accept some, and therefore you get some heat as well, but that's not visible, that's infrared. But there are some parts of the spectrum that are definitely dangerous. You do not want to stand in front of X-rays, right? You don't want to get X-rays every single day of your life. That would be bad. That's why the dental assistant always runs away when they take a picture of your mouth. Yet no one runs away when we turn the light bulbs on in the room. It's still electromagnetic radiation, both of them. All right, so this is the charts on page 67. We're going to go into great detail. We've already seen parts of it. You can kind of recognize parts of it, but we're going to focus is the very bottom of it today. So the top part, you have your normal spectrum, right? Frequency, remember, is how many times per second the wave repeats itself. The lower frequency on the spectrum are your radio waves. The higher waves are your X-rays, and the highest are called your gamma rays. In between, we have our visible light. Visible light always, it appears to take up a large part of the spectrum. It doesn't. It's just that that's kind of important to us because we have eyes. So it always is a blown up portion of the spectrum itself. This chart gives a really good and intentionally correct visualization of the visible light spectrum. It's that one little tiny sliver right there in white. Notice gamma rays takes up a large part of the spectrum. Radio waves takes up a large. Visible light is only a very small, yet they always have an arrow and it blows it up and makes it huge. It's actually quite small. Wavelength, remember, is how long it is from the start of the wave till it repeats itself. That's measured, well, it can be measured in lots of things. It's measured in meters in this case. Long wavelengths are your radio waves, short ones, X-rays, gamma rays. They give you a relative size of the wave itself. So for instance, they're saying radio waves, AM radios are very large, the size of Mount Everest. And they're saying that, for instance, X-rays are the size of atoms. And as you go to gamma rays, it's the subatomic, the parts that make up the atoms, everywhere in between. It's got a fingernail. And so it's saying a fingernail is basically the size of microwaves, according to this chart right here. I always question, I have to do the math, I haven't done it, whether that's the width of your fingernail or the length of your fingernail type thing.
Or just your whole.
Pinhead is the one that, okay, that one I can wrap my head around. Pinhead is your infrared radiation. So if you think of it, the head of a pin, head of the pin is not the pointy part, it's the other part. That's the size of infrared radiation. We are going to be focused on the very bottom of this. It's something called atmospheric opacity or opaqueness. We're going to spend the whole class on this one little slide right here, or one little portion of this right here. So there is no agreement, remember, on how this chart should be made up, whether you go from radio waves to gamma rays or from gamma rays to radio waves. Some books will do it by wavelength, some will do it by frequency. Okay, so the shortest of the shortest frequencies, like how many cycles per second are your radio waves, the highest ones are your gamma rays. So that's this particular one, but it can easily be done the other way. This chart right here, I'm going to show you a couple times today. Sometimes it starts with radio waves, goes to gamma waves. Sometimes it goes gamma rays to radio waves. You'll see it both ways. As we look at this, whatever it is we're looking here at the bottom, notice we got some color and we have some white, right? And we're going to explain what that means here. The scales that you see right here, okay, pre-calculus people know about this, logarithms. Algebra 2 people, you're going to learn about this. We have something called logarithms. I don't want to get too mathy on you today, but logarithm is a scale. Let's call this the x-axis right here. We'll call this 1. And if I go the same distance from 0 to 1, so this part right here, and a logarithmic scale, yes, we call this 2, but it ain't 2.
Stop
Right.
breaking my mind,
Right.
please.
You've heard of earthquakes, right? The Richter scale, right? The Richter scale is a logarithmic scale. And what it basically means is the distance between 0 and 1, multiply that by 10, but squeeze it into the same spaces between 0 and 1. So each time you go one tick mark over, you've increased by a factor of 10. So 1, and then the next one is technically it should be, well, by a factor of 10, it should be 10, but it's not. We say it's 2. But the space from here to here never changes. It's always 1, but the actual units do change. And it's called logarithms. Have fun with that in Algebra 2. And if you like logarithms, you'll see them again in pre-calculus, calculus, and so forth.
Mr. Shardy,
Yeah.
can I scream?
You can. All right. Most objects in the universe emit some form of electromagnetic radiation. We've talked about this before. Your body right now is giving off to this room infrared radiation, right? Your body produces, in a sense, infrared radiation. We'll talk about that when we focus on infrareds. Yeah. No, I won't have this one on the quiz. All right, some common examples. All right, I don't know if you've traveled recently on an airplane. They have this machine where you literally go up and it looks like you're getting arrested, and you hold your hands up and this thing whirls around you. I don't want to shock you, and that's why there's a blue thing right here, but it literally gets rid of your clothes, right? If you don't think those people aren't looking at dare I say it, naked bodies, they're looking at basically naked bodies. It gets rid of the clothing and allows them to see what's underneath. There was a really big controversy when these first things came out. Well, clearly there are some things that are invisible and there's some things that are visible in this picture. Well, we can see the human body in all its glory right there. This is literally the same thing, just from the other side. But you can see that this person has a gun on him right here. So this machine, which uses radio waves, gets rid of the clothing, reveals what's underneath. So it turns out that parts of the electromagnetic spectrum can actually be visible or invisible to types of materials. Window, obviously right now, if I raise the screen, right, our windows are clear or transparent. How about that word? They're transparent to visible light. I mean, I can see the light out there. I can see shapes, right? However, if I put something in front of it, and you're like, well, duh, I know that. If I put something in front of it, all of a sudden I lose that ability to see through it, just like here. You put clothes on, you can't see what's underneath it. If you get rid of the clothes, you can see what's underneath of it. And parts of the electromagnetic spectrum are transparent to some materials, and a big fancy word, they are attenuated by others. We're going to write these words down here in a second. All right. So infrared radiation coming off of your body, right? It turns out that infrared radiation is transparent to some material, right? And it's attenuated, or you can't see through other ones. Popsicle's black here because it's very cold. It's not giving off much radiation. If you've never known this about your body, if you ever get a cut on your forehead, face, scalp, whatever, you bleed very seriously. Why? You have a lot of blood vessels very close to the surface on your head. I'm not sure biologically why that's the case, but it is the case. So that's why neck as well too. Notice your cheeks, not so much, but your neck and your forehead, blood vessels are pumping a lot of warm blood through very quickly. That's why. His mouth is typically should be a much hotter shape, but since they're eating ice cream, that's why it's dark. Say again?
No, it's his pointer finger.
I don't know. I've seen
that because he has 3 fingers.
Let's count. 1, 2, 3, 4.
And then the thumb.
Yeah.
Well, yeah, you can't see the thumb.
Oh, I get it. He's holding it like this. Yeah.
No, he's holding it like a normal human being. He's doing that.
It's like this.
Why would you hold it?
I think he's holding it like this.
Because he doesn't want his, I don't know.
But it's a child. They hold it weird. He's only
I don't
holding it
know.
like that.
I try. He could be flipping us off. I don't know. He could have.
I'm trying to give you a lecture on astronomy and you immediately go to,
Astronomy,
middle
we're talking
finger.
about body heat.
right.
Talking about
bodies.
All right. X-rays are very energetic particles in the electromagnetic spectrum, and they go through a lot of stuff. A lot of stuff. In fact, they go through skin, goes through lots of things. This is how you can take pictures of your brain without cutting your skull open, right? We use X-ray as that source, and we can get, this is a CAT scan, if I'm correct, I believe so. CAT scan is just a whole bunch of X-rays put together. There is no CAT in CAT scan, though. It's a computer, tomography, computer something tomography is the CAT part. All right, I'm not a doctor. All right, in our textbook, I know I've said this before, our astronomy pictures will always have this little wiggly line here. It's saying electromagnetic spectrum, and then we'll have these letters. And when you see each picture, what's in red is how the picture was taken. For instance, the one here on the right was taken with a radio telescope and a visual telescope combined together. That's a very common thing where they take it in different wavelengths, join them together to make one picture. The one here on the left, the scale right here, AU stands for astronomical units, 93 million miles times 100, right? Add 2 more zeros to 93 million miles, you get 9 billion. And this one was taken in the infrared. This is a sun, and this is either the remnants of a sun, I believe. You'd have to look it up in the book. All right, so we're going to focus once again on this picture for the rest of the lesson right here. So if you notice there's, or if you can't tell, there's spectrum from radio waves all the way up through gamma rays from left to right. And then we have these two little light things, and they're called windows. One is called the radio window, and one is called the optical window. Blue means you can't see through it. White means you can see through it. So the question is, what are they talking about? They're talking about our atmosphere. So this is our atmosphere, big fancy word called opacity or opaqueness. We'll write some things down here in a second. All right, so let's write these things down. First thing, when you can see through an object, we call that transparent. And we're going to use the word see through. Now, obviously, that kind of denotes or makes you think about your eyes. Our eyes can't see X-rays. So when we say something is transparent to this, you can see through it. We're talking about for that individual spectrum. So we're talking about X-rays. What can X-rays see through or show? We're not talking about with the eyeballs. We're talking about what X-rays can do. The opposite of transparent is when the signal, whatever it is that you're emitting, if I send radio waves, and the radio waves get absorbed by this stuff, we call that big fancy word attenuation or attenuated. If the signal goes right through the object, like X-rays through your skin, we call your skin transparent to X-rays. If light, I don't know if you can see this, right? I'm trying to shine this laser beam through my finger, right? And it turns out the visible light, well, laser beam is visible light, right? Visible light will not, unless it's super bright, will not go through your finger, right? It gets attenuated by the skin and all the other stuff. Air is all around us. Clearly, light can travel through air. This is why that green dot is now on the wall, because the air did not attenuate the signal.
I have a question.
Yeah.
So you know how moths are attracted to light?
I've heard that.
Is that because of like the heat, or do they see something we don't?
Wow, I don't have an answer to that. Don't know.
What would they see? I don't know. It's a moth.
I know that, I mean, they have those bug lights as well too, and I know, like, you know, mosquitoes, and I mean, they get zapped all the time. So are they attracted to some of those lights are like, you know, ultraviolet black lights, right? I don't know.
They actually, like, mosquitoes find us through the heat and the carbon dioxide.
I heard it was
spread.
carbon dioxide, yeah.
And
But why are they attracted to the bug lights? I don't know. Good question.
moths.
I will. That will give me something to do over lunch.
Moths
Figure that one out.
use the moon to navigate, so they
Heard that
follow
too.
the moon. So lights trick them into thinking it's just a big moon, and they get close to it.
All right. All right. Transparent and attenuated. So I'm going to use these words now to talk about the different spectrum, those four things that we saw in the spectrum: radio waves, infrared, visible light, and then higher frequencies. And we're talking about whether our atmosphere is either transparent or does it attenuate those signals. Okay. Quick tangent, right? I've been using this word. We better write this one down. So opacity or opaqueness is a big fancy word for the opposite of being transparent. If you're transparent, you can see through it. If you're opaque, you may have heard that before. If you're opaque, you cannot see through it. The door is made of wood. The wood is opaque. I can't see through that wood. The window on the door is made of glass. And it turns out that glass is transparent. It is not opaque. Now, colored glass, right, can be opaque. A welder's goggles are made of a dark glass, and it has some opaqueness to it as well, to at least a visible light. All right, so our scale, the very bottom one, the one we're talking about today, is a scale of opaqueness and relates to our atmosphere. What is allowed through our atmosphere? I mean, what signals get from outer space to the surface of the Earth? Okay. All right. There are some causes, and this needs an explanation of why do some things get through the atmosphere and some things don't. So the main cause of the reason why the atmosphere is opaque to some signal is because the atmosphere is made up of pieces parts. We got a whole bunch of Somebody help me out. What's the main constituent of our atmosphere?
Gases.
Well, I'm talking about what's the air made of. What's the main part of on the Earth, our atmosphere?
Oxygen. What was the other thing?
Atoms of
Oxygen.
oxygen is not the answer.
Methanes.
What is the main thing in our atmosphere? 70-something%. It is nitrogen. Nitrogen is the main part of our atmosphere. When we get to the planet called the Earth, called dirt, we will talk about the atmosphere in a greater detail, but not today. So there are certain atoms, certain compounds in our atmosphere that attenuate certain signals. And it relates to the physical size. You know a bell, right? Rings at a certain frequency, right? So it turns out that other objects can vibrate at certain frequencies as well, too. And it turns out that if your signal matches the frequency of that particular element, right? Hydrogen vibrates at a certain element, helium vibrates at a certain, oxygen does. And so what happens is some of your signal gets attenuated specifically for that reason. All right, there's another part to it, man, that our book just kind of throws this word out there. We have a charged sphere that surrounds our Earth. It's called the ionosphere. It's made up of charged particles. It gets charged by the sun. And it also leads to the fact that some signals can't get to the Earth. The two main reasons for the opaqueness of our atmosphere are the atoms, or the atmosphere itself is made up of atoms, and the ionosphere. These two things are why our atmosphere, to some signals, is opaque. In other words, not transparent, and it is transparent to other ones. Just as that one picture, the radio waves make the clothing transparent, but the body itself or the gun that was on its hip, not transparent. All right, we okay? All right, so this is going to be a busy slide. I need you to copy this down. This basically is the explanation of that final chart right there. There's going to be two things. There's going to be, I think, 4 or 5 things to each one of these. One is going to be the atmosphere's effect for the individual frequencies, and one is going to be, well, what kind of telescopes do we use for these signals? So the first one is this is specifically for the Earth. For the Earth, for AM radio signals and below, 100%, they don't get through the atmosphere. They get attenuated. AM radio waves do not transmit very well through the atmosphere. Yeah, you need to have these 1, 2, 3, 4, 5. It turns out that FM radio and microwave energy shoot through the atmosphere like, I don't know, what did Patton say? You guys were studying World War II.
What?
I don't remember the quote. Anyway, I won't make the quote. FM radio and microwave energy go really easily through our atmosphere. This is why our satellites transmit radio energy, not AM radio energy, but FM and microwave, and we hear them very well. I mean, all our satellite dishes use mainly FM radio. We're talking about frequency here. We're not necessarily talking about the type of modulation. Any radio person would probably give me an argument about, wait a minute, there are some radio waves that are higher frequency that actually use AM amplitude modulation, but for the sake of that argument, we'll just leave it as lower frequency AM radios don't go through the atmosphere very well, but FM radio and higher does. We get a problem. You get to heat, infrared radiation, and once again, the atmosphere tends to block it off. We study the planet Venus. Right? Venus is an extremely hot planet, not because it's closer to the sun than we are, but because of its atmosphere, and its atmosphere traps heat very well. The heat gets reflected back to the surface, and you get the cycle of it's a lot hotter than it should be. Visible light, luckily for us, we can look up, even though we're not talking clouds, we're talking about air, right? Just plain old like between me and you, air. Luckily for us, we can see through air. But a cloud, that's different, that's water vapor, right? And then lastly, when we get to the higher frequencies, the ultraviolet and the gamma, I sort of left off ultraviolet, I'm sorry, I left off X-rays there, but X-rays are between ultraviolet and gamma rays. Our atmosphere blocks those very well. Why is this important? Because this tells us, or it dictates, where our telescopes must live. If it says transparent, the telescope can live on the Earth perfectly fine. If it says attenuated, you can't have an infrared telescope here on the Earth. You point it at the sky and the atmosphere blocks the signals. So anything in red, the telescope has to either be in space or really super high up in the atmosphere. We do have some balloons that we launch that have telescopes hanging underneath of them. They go way up in the atmosphere. We do have some airplanes that have telescopes on. You're going to see this one picture. It's a pretty famous airplane called the Sophia. And it is literally used to be like a 747, a big airplane, and they cut the side of it off and they put a telescope on it. All right, so the telescope, the second part, you don't need to rewrite these words. They're exactly the same as this. You could write it next to it. We don't have any AM radio. We're talking about lower frequency telescopes here on the surface of our planet. We do have plenty of ground-based radio. I mean, you've seen pictures of them. Arizona's very large array, has lots of them. There is and it does say space, and I will say that there are some space radio telescopes. They're mostly used to spy on other people, right? The problem is that you got to build really large antenna in space. We never get it large enough to do astronomical work, but you can certainly make a large enough antenna to suck up the signals coming from our enemies. So even though this does say space, we don't really have space-based. There's lots of proposals for them, but the antennas need to be super, super, super big. Infrared, with the one exception of the Sophia, which is on an airplane, infrared telescopes are in space. We just launched the James Webb Space Telescope. It's infrared. Visible ones, we got the Hubble. That's a visible one. That's in space. There's plenty of space ones. We've talked about that one, but we can also have them here on the ground. And then lastly, there are no ultraviolet, X-ray, or gamma ray observatories here on Earth. Ultraviolet, okay, a little bit of fudge factor there. But specifically X-ray and gamma rays, those are all space-based telescopes. Starting the next section, we're going to start talking about actual telescopes. What are they made of? How are they made? What are the pieces, parts to them? How do they work? But remember, if they're on the Earth, they're in red. So radio telescopes and optical telescopes can exist on Earth, but all the other ones, for the most part, they have to be in space. Why? Because our atmosphere makes things visible or invisible depending upon the frequency of the spectrum. All right, we okay? Click, darn you. There we go. All right, quick tangent about this dude, Faraday. British guy, really interesting story. Looks really creepy in this picture. So here's a younger painting of him who doesn't look so creepy. Michael Faraday, maybe you've heard of him, maybe. I have no idea what he has in his hand. It looks like a gun.
It's a PowerPoint clicker.
It's a PowerPoint clicker, I agreed. Oh, he does look that way. Seth, middle finger or no?
That's wonderful.
Okay.
Dumb.
You brought it up, not me. All right. So Michael Faraday has an interesting story. He was born, he was never educated, self-educated man, ends up being a kind of smart guy, gets noticed because he's smart, and a very well-educated man hires him to be his helper. Turns out that the guy that hires him, his name is Davies, I believe. Davies, this is in the 1820s, 1830s, when laughing gas was all the rage. And Davies was one of the chief scientists to investigate laughing gas. You know what laughing gas is, right? So he basically, nitrous oxide, breathes a whole lot of it, and he wants to see what's happening. He was a chemist. Davies was a chemist. He also experimented with some dangerous chemicals and kind of blew himself up a little bit, caused himself to almost go blind. So he can't do the experiments all that well anymore. So he hires Faraday to do the experiments for him. Faraday, smart guy, right? Does a whole lot of reading. He's an avid reader, self-taught person. Davies and Faraday both hear about this thing called electricity, right? Not only was laughing gas all the rage, but in the early 19th century, all of a sudden, electricity is something that's being widely studied. Faraday was one of the groundbreaking scientists for electricity. Long story short, maybe you've heard of this, maybe you've not. You heard of something called the Faraday Cage before? This would be a teacher's dream to have these things. You know what a Faraday cage is? All right.
I've seen Faraday cages.
So today we are going to learn about electrostatic shielding and Faraday cages and why it's not such a bad thing if you're in a lightning storm as long as you're inside a car. And I don't want to do that with me, so we're going to do it with Benjamin. Here we have Benjamin Franklin wearing a nice little Hawaiian hula skirt made of tinsel. And he is about to be in a thunderstorm. We are going to make our thunderstorm with our Van de Graaff generator. You can think of the belt and the Van de Graaff generator going around like this as analogous to the air circulation underneath the thunderhead as the thunderhead builds up. And then you can think of this up here as the analog of the cloud. So as soon as I unground this, it's going to start charging up. And you see Mr. Franklin there getting a little bit uncomfortable. You see his hula skirt streaming out behind him as he is in right now in quite a large electric field. As you can get a sense there, he's not so happy at this point. Maybe I'll turn it up even higher. There you see, well, I've got a lightning bolt going to my grounding rod, and as you can look at what's happening to Benjamin as the lightning bolt hits the grounding rod. There you go. Benjamin is not happy. So now what we're going to do is we are going to have the same thunderstorm, the same electric field, but we are going to put Benjamin in a Faraday cage. So to put him in the cage, I'm going to start by turning this off, and we'll ground him. And here's my Faraday cage right here. I'm going to put Benjamin in the cage. Here we go.
Faraday cage is basically just fine chicken wire. It's metal.
Okay.
Cage
Benjamin's
can
going to
be
be in the
in
same
any
spot
shape
that he
as
was
long as it
before, same
completely
tinsel skirt that he
encircles the
had
object.
before, but this time he is in a cage. Like, for example, if you're in a thunderstorm, but you are safely in a car. So let's see whether it is indeed
Cars
safe.
act as Faraday cages.
And here we go. Let's turn on the thunder, or the lightning rather. Let's turn on the lightning. Now, if you look, you can see that there's lightning hitting the cage. There's that lightning bolt going from the Van de Graaff right to the cage here. And you can see that the cage has a very considerable electric field on it. If I look at the tinsel over here on the far side, which is streaming out behind it, just like the tinsel on Benjamin was before. But now look inside at Benjamin in there. I have to be careful not to touch the cage. But now look inside at Benjamin in there, and his tinsel is completely motionless. Benjamin is completely comfortable in there.
It turns out
calm,
the Faraday cages, here's one that costs $24,000. Faraday cages block all electromagnetic radiation in the form of radio waves, right? We use Faraday cages for many. I say it's a teacher's dream because no one can operate their cell phone inside of a Faraday cage.
I see.
So when this school was constructed, I said, yeah, make every class from a Faraday cage so that your cell phone won't work. But then the Wi-Fi doesn't work either. Okay? Why did I bring this one up? Here's an everyday example of attenuation. So electricity, radio waves are in the electromagnetic spectrum. If you surround yourself by a wire cage completely, it can't be, I mean, the spacing has to be pretty fine. No electrical signal can get in and inside the cage, even though for visible light, you can see into the cage. This one is black because they use this for, this is a mobile Faraday cage. You're like, why would anybody need this? So no, it's mostly for politicians or something. If they want to have a conversation and they know it's not being recorded, then they go inside of this, inside a Faraday cage to make sure. Could scientists use one if they want to block out anything? They're doing an experiment. They don't want any radio waves to interfect that one. But this one right here, this is for specifically for keep people from spying on you. Hey, somebody hacked my cell phone. So even though it's turned off, right, when I'm talking to you, you know, enemy person turns it on, and listens to our conversation, that sort of thing. So you'll see politicians like the president travels with one of these, so that if he ever had to have a conversation without anyone listening, obviously you can hear the voice, but you can't record or anything like that from the outside. Okay, enough of that. Here's one for your cell phone for those paranoid people that like, I don't want my cell phone sending signals. You can buy for $50, you can buy a Faraday cage for your cell phone. Yeah.
If I touch the cage, would it tase me?
Only if you had a Van de Graaff generator next to it, right? Interesting point there that he made about last tangent. We'll get on with it. It is, remember, I tried to make you smarter than most people in the world here. If you ask the most common person, there's a lightning storm, you probably already heard it. You might think this as well right now. You get in your car because your car's got rubber tires, electricity doesn't go through rubber. Think that one through. Where's the lightning coming from? What's between above and the ground? A whole lot of not metal, but a whole lot of air. I mean, the cloud could be 30,000 feet above you and a lightning bolt, boom, kills you, right? There's a whole bunch of air between the cloud and the ground. How did the lightning go through the air? Air is an insulator, just like rubber. You're telling me that the lightning bolt going through the air is going to give one care about your little tiny piece of rubber? The lightning bolt isn't only going to go through the rubber, it's probably going to light the rubber on fire. So the question is, why do they say get in your car? It has nothing to do with tires. It has everything to do with the fact that your car is made of metal. Your car is a Faraday cage. And just like the video just showed, when you have lightning bolts striking, the lightning bolt will strike your car, but it's not going to get you because you're inside the cage. So yes, cars are where you should be during a lightning storm, not during a tornado, but during a lightning storm, and they will protect you, but it has nothing to do with the tire. It has everything to do with the fact that the car is a Faraday cage.
People actually thought it was because of
Ask the common person, why do they tell you to get into a car during a lightning storm? And I'm going to claim that 99% of the people in the world will say, well, it's because the tires are going to protect you from, getting hit by the light. No, it's the metal of the car.
My father's always told me it's the rubber.
I know it's wrong. Don't tell your father he's wrong. All right. Back to the whole purpose of this. Remember, the whole purpose of this one lecture right here is to talk about signals, not just radio signals, but all electromagnetic spectrum for certain parts of our atmosphere get attenuated, just as clearly the guy is wearing clothes right here, but according to the radio waves, went right through your body. This is literally why in my pants right now, my cell phone, hopefully yours is in my pants, but your cell phone does the same thing. Your cell phone clearly receives stuff while it's in your pocket because your clothes, the cloth itself, is transparent to radio signals. Your clothes are not transparent to visible light, unless it's a really thin material, but it's certainly transparent to radio signals. Last one.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day,
All right.
everywhere you go. It is odorless and tasteless, yet you use it.
See you guys tomorrow.
Hopefully there's a snow day tomorrow.
And Ethan, if you have any questions, hopefully about what to write down, hopefully was apparently clear in the video. See you tomorrow.